Hello students, welcome to another video of metric space. Today we will start the new topic of the last topic of our this chapter, which is bounded set. Bounded set. A subset of metric space XD is said to be bounded whenever that set is contained in any open sphere. This is the very simple definition of bounded set. Definition of bounded set is a subset suppose a subset A of metric space XD is said to be bounded set if there exists some element, suppose x naught, in metric space XD and some radius r greater than 0 such that the A is totally contained in that open sphere SR of X. This A is contained in SR of this X naught. A subset A of metric space XD is said to be bounded if there exists some element in metric space such that if we consider that element as a center and then there exists some radius r and we draw the open sphere, then that open sphere around that X naught contains A, that is A is totally lies inside that open sphere, then we say that A is bounded. So this is the definition of bounded set. A subset of metric space XD is said to be bounded whenever that set is totally contained in any open sphere. Now the next definition is diameter of a set. Diameter of a set. Diameter of a set. Till now we have seen the diameter in circle, that is 2 times radius of the circle is called diameter, but in metric space there is some another definition of diameter of a set. So definition of diameter of set, let suppose A be a here diameter of a set, and previously we have seen the diameter of circle. Now here diameter of some set. Till now we don't have seen the definition of diameter of for any set. So here we will see the definition. Let A be a non-empty subset. A be a non-empty subset of metric space XD. Suppose this is non-empty subset of metric space XD. Then the diameter of A diameter of A is denoted by this notation, diameter of A. Diameter of A denoted by this notation and is given by that is diameter of A is given by supremum of distance between x and y. Supremum of distance between x and y such that these x and y are the elements of A. So diameter of A is defined as supremum of distance between x and y. Suppose this is metric space XD, and if we take suppose this is the subset A, which is this A is subset of metric space X. So this is metric space XD. Now diameter of A means the maximum distance between. We have to check for each and every element of these x and y, and if we get the maximum distance between any 2 points, maximum distance between any 2 points of the set is nothing but diameter of that set. So here if our A is, suppose this is A is open set, so there that open set contains only interior points, so this may be the largest distance between these 2 points, so x and y. Supremum of distance between x and y for all x y belongs to A. For every pair x and y, we have to find the distances among that x and y, and supremum, that is the maximum distance between. maximum distance of xy is nothing but the diameter of set A. So this is the definition of diameter of A. There is no need to draw this diagram. So the next example and the most important one is show that a subset A is bounded. Show that the subset A is bounded if and only if it is either empty, or its diameter is finite. So that a subset A is bounded if and only if it is either empty or its diameter is finite. This is the standard definition of bounded of set. Bounded set means that set is either empty or its diameter is finite. A set A is said to be bounded if it is either empty or its diameter is finite. This is the standard definition. This is the standard definition of bounded set. This is the standard definition of bounded set. So we have to solve this example. We have to show that A is bounded if and only if it is either finite or it is either empty or its diameter is finite. Now, if given set A is empty, then there is nothing to prove because every empty set is bounded. So if A A is equals to 5, then there is nothing to prove. If A is empty, then there is nothing. Now let A is a non-empty set. A is non-empty set. Now for non-empty set, we will suppose that A is bounded, then we will prove its diameter is finite, and conversely its diameter is finite, then that set is bounded. So A is non-empty set. Suppose A is bounded. Suppose A is bounded. A is bounded means there exists some element in X and some r greater than 0 such that this A is totally lies inside that open sphere centered at X and radius r. Now we have to show that diameter of A is finite. Our claim is diameter of A is finite. Diameter of A is finite. That is, we have to show that for diameter of A means supremum of distance between any two elements of A. That is, we have to show that for any A1, A2 belongs to A, supremum of distance between these two A1, A2 is supremum of distance between A1, A2 is finite. That is finite means it is less than or equals to some element. For some any element belongs to some, for some this K belongs to R, for some K belongs to R. Finite means less than some number, then we call that supremum of distance between A1 and A2 is finite. We have to show that this number, this supremum of distance between these two, that is supremum of distance between A1 and A2 is diameter of A. Diameter of A is finite. To show this finite, we have to show that diameter of A less equal some real number. Now we will take this A1, A2 belongs to A, then clearly let A1, A2 belongs to A. This implies A1, A2 belongs to A, and here A is subset of S R of X. Suppose this is equation number 1. A is totally lies inside this open sphere. A1, A2 are the elements of A. So clearly this A1, A2 lies inside that open sphere. So A1, A2 lies inside this open sphere S r of x. This is by equation 1, by using equation 1. Now a1 a2 belongs to S r of x implies we can use the definition of open sphere. Distance between this a1 and x is less than r. Again distance between a2 and x is less than r. This implies distance between a1 x is less than r and distance between a2 and x is also less than r. Now we have to show that our claim is diameter of A is finite. That is, we have to show that for any a1 a2 this supremum of the distance between a1 a2 less equal k. So by triangle inequality we can find the distance between a1 and a2. So here a1 x less than r, a2 x less than r. So distance between a1 a2, we can use the triangle inequality and write distance between a1 a2 is less than or equal to distance between a1 x plus distance between a2 x. Now by triangle inequality distance between a1 a2 is less than or equals to distance between a1 x plus distance between a2 x. So a1 x, distance between a1 x is less than r, so we can write this is less than r, again plus this distance is again less than r, so this is equals to 2r, r plus r is 2r. This implies distance between a1 and a2 is strictly less than 2r for all a1 comma a2 belongs to a. For any a1 a2, because a1 a2 are arbitrary elements and we have proved for any two arbitrary elements a1 a2 distance between a1 a2 is less than 2r. So distance between a1 a2 is less than 2r for all a1 a2. So for all a1 a2 distance between a1 a2 is less than r. So if we take the maximum distance of a1 a2, supremum of distance between these a1 a2, then clearly that distance is again less than 2r. This implies supremum of distance a1 a2 such that this a1 a2 belongs to a is strictly less than 2r. So supremum of distance between any two elements of that set r is less than some 2r, that is some real number, implies this is the diameter of a. Diameter of a is finite. Diameter of a is finite. Finite number means we can check that number, we can find that number. So distance is some real number and the distance is less than some 2r. R is radius, that is known for us because we are drawing the open sphere by that radius. So 2 times r is a number that we can find. So the supremum of distance between a1 a2 less than that number, so clearly diameter of a is finite. Now conversely we will suppose diameter of a is finite. Conversely, suppose a diameter of a is finite. Diameter of a is finite, that is diameter of a is less than some number, suppose for some r. Now our claim is a is bounded. A is bounded, that is we have to show that a is bounded. We have to show a is bounded means we have to show that there exists some element in metric space and some radius greater than 0 such that a lies totally inside that open sphere centered at x and radius r. This is by definition of open set. Now such that this we will take one element of a, but diameter of a is less than r, so we can write distance between that element of a and suppose some a prime is less than r. Let a belongs to r, be any element of r. Then for any, suppose a prime belongs to a, for any other element of a, we have distance between a and a prime. A and a prime are two elements of a and the diameter of a is finite. So distance between a and a prime is less than r, because supremum of distance between any two elements of that set a is less than r. So we can write distance between a and a prime is less than r. because reason behind this is diameter of A is less than R. Diameter of A means supremum of distance between any two points of A. So here the supremum means maximum distance between any two points of A is less than R. So distance between any two points of A must be less than R. Now this distance between A and A prime less than R, we have to prove that A is bounded. That is, we have to show there exists some element x in X, and for that there is some radius R such that A is lies inside that open sphere. So we have to find the center A and radius R. So here distance of A and A prime is less than R. So we can write by definition of open sphere, this A belongs to S R of A prime. If distance between A and A prime is less than R, so we can write this A belongs to S R of A prime. If we take A prime as center and A is any element of set A, then distance of A and A prime is less than R, implies A belongs to S R of A prime. So here we get the center and some radius R such that every element of A lies inside this open sphere. A belongs to AB any arbitrary point, then for any A prime belongs to, or distance between these two is less than R because of diameter of A is less than R. So this distance of A and A prime is less than R implies A belongs to S R of A prime by definition of open sphere. So A was arbitrary element of A. So we can write for every A belongs to A that A lies inside this open sphere. So implies A is subset of this open sphere. Thus, since A is subset of metric space X, A prime is element of A and implies A prime is also element of X. So we have thus there exists this A prime belongs to X and R greater than 0 such that A lies inside this open sphere S R of A prime, and A prime is again element of A, implies A is bounded. A is bounded. A lies inside any open sphere implies A is bounded. Hence the solution of this example. Now the next example is show that diameter of S R of X is less than or equals to 2R. This is for your homework. Show that diameter of S R of X is less than or equals to 2R. Diameter of S R of X is less than or equals to 2R. So this example you can solve because you know the definition of diameter of A. Diameter of A is supremum of distance between any two elements of that A, and just you have to replace A by S R of X. So you can write this, the diameter of S R of X is equals to supremum of distance between any two elements of this S R of X. So for any two elements we get the distance between that, suppose X and Y are two elements, then here X is already taken, so Y and Z are two elements, and distance between distance between that Y and R, we will solve this. We know that diameter of A is equals to the definition of diameter of A, supremum of distance between xy for all xy belongs to that set A. So we have to replace A by S R of X. We can write diameter of S R of X is equals to supremum of distance between, here X is already taken, so we will take notations Y and Z. Suppose Y and Z such that is Y and Z are the elements of here S R of X. Now this Y and Z are the elements of S R of X. Y and Z belongs to S R of X implies distance between this Y and X, that is X and Y or Y and X is less than R, and distance between x and z is less than r. So we can find distance between y and z. We have to prove the diameter of s r of x is less than or equals to 2r. So here supremum of distance of y z. If we find the distance between y and z, we can find distance between y and z by triangle inequality. By triangle inequality, we can write distance between y and z is less than or equals to distance between y and x plus distance between x and z. So distance between y and x is less than r plus distance between x and z is again less than r. So this is equals to 2r, implies distance between y and z is strictly less than r plus r is 2r. Distance between y and z is strictly less than 2r. So strictly less than distance between, for any y and z belongs to that open sphere s r of x, distance between y and z is strictly less than 2r. So if we take the supremum of distance between y and z, this supremum of distance between y and z for any y z belongs to that open sphere s r of x, then clearly the supremum of distance between is again strictly less than 2r, strictly less than 2r. So we can write this as diameter of, this is the definition of diameter of s r of x, and we can write it as less than or equals to 2r, because here any number is less than, strictly less than, then we can write that number is less than or equals to. Less than or equals to sign implies either less than or equals to. Here clearly we can say that it is less than, so less than or equals to. We can, there is no difference if we write less than or equals to. Hence the solution.